Yeah, I want to talk to you today a little bit about Passport and how we're using Silicon to secure your Bitcoin. So next slide. So what is Passport? Well, it's our next-gen Bitcoin-only hardware wallet. It's fully air-gapped, so the only communication paths are really QR codes. So it does have a camera and a color screen and micro SD. So we don't have right now Bluetooth or NFC or Wi-Fi. At least on this generation device, I don't think that's something we would do. I think we'll always have an air-gapped device. So improvements over the previous one, color screen, removable lithium-ion battery. We had AAA's last time. USB-C connector now to power the device, so you can use it while it's plugged in, which you couldn't do before. That's power-only pins though, so we preserve the air gap on that. And it's just a newer, slimmer design, sort of fancier design. So some of the philosophical points we have are to be as transparent as possible with, open source software, open source circuit designs and schematics, bill of materials. That's all online on our GitHub right now. We only purchase components through reputable suppliers and distributors, almost always through US-based companies right now. And we're trying to make use of generally available components. So there's no really weird, funky components that would be hard for you to acquire if you wanted to build your own Passport from scratch without our knowledge or permission. Next. And the last couple of things are, like everyone else has been talking about, we're trying to minimize the use of black box silicon, that is, chips running unknown firmware. We get really nervous anytime there's a big binary blob that we have to trust. And Bunny's solution for that, putting things into the untrusted zone is kind of the same approach we're taking, where as much as possible, we treat that as a dumb transport if it was some kind of, like Bluetooth, Wi-Fi, NFC. Otherwise, we try and run code that we wrote ourselves or that we've vetted and inspected. We also assemble everything in the US, including the circuit boards. So what do we use for silicon? So we use the STM32H753. It's a pretty powerful 480 megahertz processor. And we use that in combination with the ATEC 608A Secure Element. Those are connected over a single wire serial channel. And the rest of this talk, we're just going to talk about how these components are configured and used for Passport. But first, a brief interlude about supply chain security. And so what this talk isn't about is a lot of details on the complexities that are the entire supply chain. So, obviously it would encompass everything from where the components are made to proof of custody along the way to our factory, to who's on the manufacturing floor at our factory, and all, shipping and to when the consumer finally receives it. Of course, security at each of those steps along the way is important, and we do things for that, but we're only going to talk about the silicon stuff today and what happens after the chips get to our factory. So obviously, first thing is we're assembling these things into boards. We got a pick and place machine that puts them onto PCBs. Then they go for testing and provisioning. So we created our own custom bed of nails fixture that lets us connect to test points over GPIOs on the boards. So this lets us do a bunch of things to verify that the board was assembled properly, the voltage levels are right, and allows us to program the bootloader and the firmware for each PCB. And we wrote a custom tool for this in Rust to control the fixture and the provisioning. Since this is an important step, we wanted to be as in control of this process as possible. There's a lot of MCUs that will come with the ability to program them from the factory or from the chip vendor, and we didn't want to rely on any of those tools that they were providing. So the first thing we do is we load a test bootloader onto the MCU, and we run through a series of hardware tests. And this is really just to make sure that everything was assembled properly. So we check screen controller, keypad controller, secure element, basically making sure we can communicate with everything. And then here's one of the first important steps for security is we have a supply chain secret that's copied to Passport. we'll have some details on this later. One thing we didn't do for this round, which we may change later, is we didn't want to have a per device unique key that we would have to remember, because there was some concern from some people that we would be tying this unique ID to somebody's, physical address or email address to associate a unique ID with them that we could at some point in the future use to associate, future transaction data. Of course, we flash the normal bootloader and firmware and restart Passport, and then during the first boot, Passport's going to configure the MCU and secure elements, as we'll talk about next. So the first thing we check to see if we've configured it already. The MCU has a section in Flash, the bootloader Flash, where we store the secrets. And we'll talk a bit about them again the next slide. If we've configured those, if we haven't configured them, sorry, if we have configured them, we go to the normal boot processing. If we haven't, obviously we'll go ahead and provision them, as we'll see next. And then the secure element also has to be configured. And there's two aspects to this on the chip that we're using. There's the slot configuration, which is what is each slot used for, and how is it protected? Like, is this slot readable? Is this slot writable? And under what conditions? So we configure that. If it's been done already, the bootloader skips ahead and boots up as normal. Otherwise, we'll cover those slots down below. Next slide. So on the first boot of the MCU, we generate a random one-time pad and a pairing secret and a transaction cache encryption key. Random numbers on Passport are actually using Bunny's avalanche noise source. So thanks for that, Bunny. Of course, like him, we're pairing that with other sources of randomness that we XOR together, including potentially the MCU and the secure element. And these are just basically stored into the internal bootloader Flash once they've been generated. And the pairing secret, as we'll see, is also stored in the secure element. Next slide. So this is a bit of a visual overview of how we've configured the slots. There's 15 of them on this particular device. Slot 8 being a particularly large one that we didn't actually have the need for at the moment. So we've got pairing secret, a pin stretch, random number, a pin hash, which is the hash of the user's pin, a pin attempt random number, which is also used as part of the hashing process we'll talk about, some login counting information to restrict how many attempts the user has to access the device, the supply chain private key that we talked about, we talked a little bit about earlier, the user's Bitcoin seed, obviously that's important. And we'll talk about all these in more detail, but as a quick overview. There's also a firmware PUBKEY that allows you as a user or developer to load your own code. Some last firmware timestamp to help prevent downgrade attacks, and then a hash value that we're using to make sure that the firmware that's loaded on the device is what it's supposed to be, and that's what the SE uses to turn on a secure GPIO that turns an LED from red to blue. Next. And so yeah, next we'll just go ahead and cover some details on these. So the pairing secret, the SE, this pairing secret is used to prove that the secure elements in the MCU are a matched set. So as others have sort of mentioned, you want to make sure that you can't swap out the SE or the MCU or both and have a functioning system. Obviously if you extract or swap out both of them, you're sort of starting from scratch and you wouldn't have access to any of the secrets anyway. So without this pairing secret, if either side were to be changed or lose access to the secret, then you can't communicate with the secure element. And so there's this little back and forth dance that we do to prove that we have knowledge of the secret using an HMAC. So once you've done this process, then you're able to issue the next command, which is, now that I've proven, I know who you are and you know who I am, what slot do I want to read or write? And this process happens every single time we want to read or write a slot. We have to repeat this and prove who we are again. Next. So this slot, we contain a pin stretch number, and this is a value that we just asked the SE to repeatedly essentially hash the user's pin. And we do this partially to make pin attempts take longer. So we just repeatedly hash it to take up a little bit of time on each pin attempt. Next slide. And then we have the user's pin hash itself. Actually, if you go forward to the next slot temporarily, the pin attempt hash is a secondary random value that we use to help prove or help limit the number of pin attempts. We hash it with the result of the key stretched pin that was used from slot 2. So we go back to slot 3 temporarily. Yeah, so then we've taken the user's pin, we've key stretched it with the slot 2 value, we've hashed it now with the value from slot 4, and we now, assuming, so from the first example, on the first time the user sets the pin, we've done the hash, then we XOR it with the one-time pad value that was stored in the MCU's flash. So this is an encrypted version of the pin hash even. So even if they were to reverse engineer the SE or like decap it and extract the values, they still would not have access to the pin. And what's important is that, as you'll see, if you go back up quickly to the graphic, Chris. Yeah, so you can see here, a lot of these slots have an arrow pointing from a slot to slot 3. And what this means is that they require further authentication from slot 3 in order to read or write them, depending on the particular slot configuration. So what that means is, in addition to the unlocking dance that you do with the secure element, you also have to do an unlock essentially to prove that you have knowledge of the pin. And so you can't read or write any of these slots that are marked in green without having proven you know the value of the pin hash. We can go back forward down to slot 4 again. All right, and so the other thing, this value is only readable if the value of the monotonic counter, which is part of the secure element, is less than the match count. So as the user enters pin value or pin attempts, if they get them wrong, we increment the counter. Every time we read this pin attempt hash, we are counting a pin attempt. And so if you just keep doing that, you'll eventually run out of attempts, and then this value is no longer readable. And that will mean you'd no longer be able to prove the value of slot 3. And so all the other slots would be inaccessible to you. Next slide. This one is probably not necessary anymore, but it just keeps track of the last login counter. We just use this to show the user the number of failed attempts, but I think we can actually do without it. It doesn't actually have to be in the secure element. Next slide. As I mentioned, the match count. This is a little bit of a weird thing, but it has to be a multiple of 32. So every time you successfully log in, we have to bump this to a multiple of 32, which means we have to bump the monotonic counter up. So if we say allow, I think we allow 21 attempts. So we'd have to bump the counter up until it was 21 less than the match count, which is a little bit weird, but that's hardware for you. Next. So this is important. This is a supply chain private key. And if we don't have to necessarily go back up, but on the visual overview, this slot is marked as not readable and not writable. So after we've configured the slots, this value can't be read by the MCU and it can't be modified. And so we use this in a process that we'll describe later on in the supply chain section to do an HMAC challenge response with the Foundation validation server to prove that this passport is genuine. Next. So this is the user's seed. So the user's entropy bytes are in here, and they are the byte values that we typically use to look up your seed words. And these are XORed with the one-time pad from the MCU before storing it. So again, if you were to remove the secure element and do whatever laser fault attacks or whatever you want to do to extract that, you would still get an encrypted version of the seed, and you would still need to compromise the MCU. But of course, the MCU is easier to compromise than the secure element, but every little bit helps. And I'll have another comment about one thing we're going to be adding to improve this later. User firmware PUBKEY. This is just the user can choose to trust another public key or another essentially trust a private key by having the public key. This is for advanced users who want to burn their own firmware, or for developers who you want to do some experimentation on Passport. So the bootloader will only install and load firmware that's either signed by our foundation keys or signed by the public key that is in this slot in a secure element. And only a user who's proven knowledge of the PIN, in other words, logged in, is able to install this PUBKEY. So slot 11 is the firmware timestamp that we most recently installed, and it's only updated when installing foundation signed firmware. It's not updated when you install a custom user build or any of our beta releases, because essentially our beta releases rely on the user firmware key as well. So the bootloader won't actually install any officially signed firmware that's older than this timestamp to prevent downgrade attacks. And this is the hash we use to turn the security LED from red to blue at boot. This is a combination of the firmware hash and the device hash. The device hash is a amalgamation of the secure element serial number, the MCU one-time pad, the pairing secret, and the MCU's unique ID. And by combining that with the firmware, essentially if any of these things changes, the security LED will not turn blue on boot, and you should not continue to use your device. And again, this value is updated whenever we install a valid signed firmware image. Next. So just to quickly touch on supply chain validation now. The slot 7 contains the private key, as I mentioned above. And there's two methods that we use. One is a manual one, which was the only one that we had for our first gen Passport Founders Edition. But we've also recently released a mobile companion app called ENVOY. And we use the mobile app now for the newest version of Passport, which is the one with the color screen. And this is the preferred method, obviously, if you have the newer device. Next screen. So in the manual version, which you can still use this on the new Passport, if you happen to be a user who doesn't want to install our mobile app, you can still validate using the old manual process. And you do that by going to our website. We also provide the QR code for this on Passport during the validation process, so you don't have to type it in necessarily. So either on your phone or computer, you go to this website and we generate a random challenge and we hash it with the supply chain private key. And we sign the challenge with a separate private key of the server. Passport knows the corresponding public key that's baked into the code. And the user scans this QR code with Passport, and Passport then goes and says, "Hey, was this signed by the foundation server?" Yes. Then it asks the MCU, the secure element to perform the HMAC on the challenge and generate the response. And from those response bytes, we essentially do the same process you would do to look to turn the bytes into a BIP39 seed, and we show 4 words that correspond to the first 4 words of that phrase. And if those words match up, the user enters those 4 words on the validation website, and it knows what those words should be if the Passport knows the supply chain private key, and it tells you whether you pass or fail. Next slide. So it's a similar process for Envoy, except that the user doesn't have to do the typing. Envoy fetches and doesn't have to navigate to the website. The user goes ahead and fetches a random challenge from the server directly and presents that as a QR code on your mobile phone. And then the user scans the challenge with Passport. And again, Passport does the same process. It checks that it was signed, performs the HMAC, turns it into a response. And the response is then scanned from Envoy, and Envoy sends the response data to the Foundation server and receives a pass or fail result, which Envoy then displays to the user. Next slide. Some of the future improvements. So that covers, the supply chain and the slot configuration. Some of the future improvements we have are that with slot 9, which is the secret seed value, we're planning to encrypt that further with essentially with the user's PIN. So right now we store a PIN hash in slot 3. We're going to take an alternate version of this PIN hash and XOR the PIN hash with that as well, because that means now you have to also know the PIN. So even if you compromise the MCU and you compromise the secure element, without knowledge of the PIN, you still can't decrypt the seed. So you'd still be looking at a brute force attack on the PIN even after you decrypted it, or even after you obtained the value from the secure element and the MCU. Also, the secure element library that Microchip provides incorporates a PKI features, or some PKI features. And they use this part in a lot of sort of supply chain validation processes. And like, for example, I think like laser toner cartridges are using this to prove that the part is genuine. And so we're investigating that as a possible way of doing supply chain validation in the future. Next. And those of you in the know may know that there was a 608A and a 608B. There's supposedly some improvements to the B variant, but the level of the improvements is really not disclosed by Microchip, even though we're under NDA. So some people think it provides additional resistance against laser fault attacks. So we are going to be updating to that version on the next batch of Passport devices. So it's not all better though. This device is actually slower at some operations overall, but other than timing, it's a pin compatible upgrade. And so even if it were only for the marketing perception, it seems to be a good idea to upgrade to it. Next slide. Silicon dreams. So we've been sort of asked, what would we want in sort of an ideal secure element in the future? Some of the limitations of the current secure elements are that it supports a small number of seeds or secrets. So we'd want to be able to have, potentially, dozens of root seeds that we're protecting. There's also only a single monotonic counter for this, which would limit you to a single pin. And so it might be nice to have, other monotonic counters available or equivalent functionality to be able to keep track of separate login attempts on different pins, although that's debatable. Obviously, running crypto on chip. Right now, our secure element is really dumb compared to the kind of secure elements that Chromium is talking about developing, which are able to execute arbitrary code. Ours just has some built-in features for hashing and HMAC and storing values and retrieving values. But if at least being able to do signatures in the SE would be fantastic, so we don't have to have as Simon was saying, they temporarily bring the secret into memory. We have to do the same thing and then erase it as soon as we're done with it. It would be great to not have to do that. And then having the MCU and the SE on the same die or in the same package could be good. And I know that seems to be the path that Chromium is on. Ours are separate right now, and we kind of like it that it's separate. I'm not sure that in some ways it's nice that they're separate for separation of concerns and that there's no way for them to interfere. But it might be nice if they could maintain their separation but still be on a single BOM item, single chip. Next. I already mentioned this, monotonic counters would be good, more monotonic counters, and possibly configurable rate limiting to control pin attempt frequency. I haven't thought about this too much as far as how you do it in the hardware. Right now, we're limiting pin attempts mainly by key stretching and performing time actions that take time in the chip, and maybe this is just the best way to do it. But it'd be interesting if there were other mechanisms that maybe wouldn't use as much power. And then this was an issue early on, but like being able to dump the internal state of the secrets might be interesting for a developer version of the SE. To make sure, because like it's a black box, and sometimes when you're doing something wrong, it can be hard to tell what you're doing wrong. But it, you know, like if I could just see what the value was in there, maybe it would tell me what my code is doing wrong. And that's pretty much it.